So just a few quick housekeeping notes. So short session today, we'll just do your presentations. And then if you guys have any questions on the brain lecture from yesterday, I can answer those. Otherwise, we'll just plan to have our last Zoom session on Wednesday, assuming that that is going to work for everyone. If for some reason I'm not able to be here for that session on Wednesday, I'll just have you guys email me your presentations. Because the only thing that I'll have left to grade next week will be those presentations. Everything else will be on those eLearn quizzes that will grade themselves. I will still plan to submit your final grades as quickly as I can. I think they're due like the Tuesday after class ends. So class ends on the 17th, and I think they're due kind of that following Tuesday. So assuming that I get the lab reports graded today, I should be set to have everything graded fairly easily. And next week is pretty light for us in terms of work and stuff like that. So we won't do a Zoom on Monday. We'll just plan to do Wednesday for the XPhys projects, those presentations, and then you have your final exam on next Friday. Any questions on anything? Everybody's good? Okay. So we'll start with Jess and Valerie. You guys want to start?
Sure.
Okay.
It says you need to allow me to screen share.
Oh, yeah. Okay, I think you're good.
All right, can you guys see it?
Yep.
All right.
Okay, so today Jess and I will be talking about environmental physiology lab and how the subject's heart rates compared in a hot and cold environment. So first off, the purpose of this experiment was to compare physiology changes in a simulated hot environment and in a simulated cold environment. So more specifically for Jess and I, the purpose of this was to compare subject heart rates in a simulated hot environment and in a simulated cold environment. So our hypothesis was, does heart rate increase more in a hotter environment compared to a colder environment? And just a little background on cardiovascular drift before we really dive into this presentation. So cardiovascular drift can be defined as the upward drift of heart rate over time, coupled with a progressive decline in stroke volume and the continued maintenance of cardio output. Cardio drift occurs while exercising intensity remains constant. So we can see this occur 10 to 15 minutes into a constant exercise. And then this is where we may hit like a plateau where both the blood and oxygen are being supplied to our internal organs and body at a constant pace or effort. And then, however, after this plateau, there can be no increase in the pace or effort, and yet the heart rate can still be increasing for like the next phase of exercise, or about 20 to 30 minutes into the exercise. So there will be no change in cardio output due to like the decrease in stroke volume and the heart rate increasing. And the heart rate must continue to increase because since stroke volume is decreasing, and this helps maintain like a constant pace or effort in exercise and cardio output. And so, however, going past the maximal exercise, this does not give the cardiovascular system enough time to completely fill the heart with blood, and thus resulting in like a decreased stroke volume. So we do this to get rid of heat in a hot environment. So, and because we always need to regulate our body temperature and core temperature as well. And And so we see this more commonly in a hot environment. We really don't know what the certain cause of it is, but we do see this more in a hot environment because we push the blood closer to the skin for the heat to dissipate out. Okay. And then,
All right. Were you done with that slide? Oh dear. Can you guys hear me?
Yeah.
Okay. So for the methods to test this out, we had subjects walk on a treadmill in 2 different sessions. The first session was hot, so we had them wear a sauna suit and a stocking hat to try to keep the heat in. So we had them start at walking at a low intensity and then slowly increase to moderate over time. And we took their heart rate at right before exercise, and then 3 minutes in, 6, 9, 12, 15, 18 minutes in, and then also 3 minutes after exercise. And then we had to just make sure that the subjects, if they got like lightheaded or dizzy or like not feeling well, just to like stop, because if you get hot, overheated easily, that would be not good. And then just make sure that they hydrate really well so you don't get too dehydrated. And then next, we had the subjects do a cold session. So wear like lightweight clothes and then wear ice packs under a baseball cap. And then if girls wearing like a sports bra like at the front end, and the subjects were told to use the same intensity as the hot walking session, just to make sure that you're not like increasing your intensity a lot. So then that would just change your heart rate because of like that, not like the actual temperature. And then again, just make sure that they're keeping it hydrated. And then to analyze the data, we use Microsoft Excel, and we use an unpaired t-test because we're using 2 subjects, but just like 1 type of data. And then I have 2 different graphs to show here. The first one in cold, which is the orange. I couldn't figure out how to switch them around, so that's just how it is. And then we used a one-tailed unpaired t-test because we're looking at like the overlap only one way, it's not going both ways. And then the p-value ended up being 0.09113. So that isn't the normal, like, it's not, how would I say it? Like the normal, we usually use like 95%. So like this wouldn't be significant at 95%, but it is at 90 since it's still under 0.1. So it's not as significant as it like the people you typically use. So it's just 90%, it would be good. And then I thought this box and whisker plot was really nice to look at, like the ranges that they came from. So here's like most of the data, and it went all the way out to the outliers here, so you can see most of the data for the cold is lower than the stuff for the heat. It's significantly lower in here. So yeah.
okay, so we did find a p-value of 0.09, which was like greater than 0.05. So findings were not as significant as we thought they would be. But looking at an article on Wingo and Curtin, like they kind of did the same like setup as us as far as testing subjects like cardiovascular drift and like VO2 max in a hot and cold environment. So they want to assess the relationship and causation of VO2 max and cardiovascular drift. And so they created a study where they measured the subject's VO2 max on the same time the cardiovascular drift occurred. So they took 10 men, asked them to cycle in 35 degrees Celsius or 95 degree Fahrenheit, and they wanted them to do this at 60% VO2 max, or within like 75% of their maximum heart rate for 15 minutes. And then they wanted them to cycle at 45 minutes with no cooling, and then 45 minutes with a fan, beginning at approximately 18 minutes into the exercise. And then after each bout of exercise, it was immediately measured. The VO2 max was immediately measured to show how hard their hearts were working too. And so what they found in a no cooling environment, their VO2 max decreased 18%, their heart rate increased about 16%, and their stroke volume fell 12% from 15 to 45 minutes. And then with a fan, such like in a cooler environment, their VO2 fell about less than 5%, and then their whole heart rate rose about less than 4%, and then their stroke volume decreased less than 3% from 15 to 45 minutes. And they say that the fall in VO2 max is associated with the cardiovascular drift during exercise in a hot environment, and this is affected with body cooling through the fan airflow. So, so their overall findings support that a causal link between cardiovascular drift occurs during exercise in a hot environment and decrease in VO2 max. So their findings kind of are similar with our findings, because they did find that the men's heart rates did increase kind of significantly with their study in a hot environment, and we kind of found the same thing with the two subjects, heart rates increasing in a hot environment with our two subjects, heart rates increasing in a hot environment as well. So some errors within this study, within like our study, is we didn't really track like record gender. So I know like gender can play a fact, because apparently women have a more they can handle heat better than men can, and like their heart rates will go up. And then the speed and grade varied among the subjects, and some subjects may have used heart rate monitors and Apple Watches. So just some human errors with that. And these are our citations for presentation. Thank you.
Awesome. Thank you, ladies. Taylor, you want to go next? Unmute yourself, please.
I'm sorry, I'm so bad with that.
Okay.
Let's see. Alrighty, so this is our presentation. And Sia is going to start off talking for, I believe, the first 2 or 3 slides. Ooh. Well, hold on a second.
You got a lot of tabs open.
I know I'm really bad. I'm not the most organized person. So it says like I need to request access all of a sudden.
Is it under yours or is it under Sia's or?
Well, yeah, so Sia started it, and then I was just listening to her stuff this morning, so I don't know why it's saying that I don't have access.
Maybe X out and try it again. I don't know.
I don't know why it's saying that.
Do you want me to text her real quick?
Sure, I can too. Because I can wing it too.
Let me pull up Alyssa and Jelani's, and then hopefully she'll get back to you. How's that sound?
Okay. Sorry about that.
Oh, it's okay. So let's see here. Where did I have that? Here it is. We'll see if theirs works. Theirs is a same thing here.
Environmental. Our hypothesis for methods, our results show in our article. So
That was really fast. That was a really fast presentation. How do I, Did you guys hear that?
Yeah.
Yes, okay. I wonder why it does that.
our for methods we use repeated measures and NOVA.
Okay. I'm gonna give it one more whirl here. I wonder if it's something with Zoom. I don't know. Because when I don't share it with you guys, then then I can hear the whole thing.
Environmental. Our hypothesis for methods, our results show in our article associations between thermal and physiological responses of the human body during exercises. Environmental physiology essentially talks about heat and cold and how our bodies react to that.
Can you guys hear it?
So starting with heat,
Yeah.
Okay.
body has 4 ways it can lose the heat. 1 being conduction, 2 convection, 3 radiation, and 4 evaporation. So radiation is pretty much just the electromagnetic heat waves and how our bodies absorb those. Conduction involves direct heat transfer from one molecule to another liquid or solid or gas. Convection is the movement of gas or liquid over the skin surface. Evaporation is pretty much just water vaporizing from respirator passages and the skin. So that's like sweating or anything like that. So for circulation, for heat, the body wants to open up the vessels and move the blood from the core to the shell. So our body wants to remove the heat from our core to try to get the heat out of our body, I guess, to get back to homeostasis. And now talking about the cold, ways to avoid the cold would be the peripheral vasoconstriction, non-shivering thermogenesis, and shivering. These are all ways to try to keep the heat to our core and not the shell. So acclimation to the cold Our bodies don't really react or change dramatically to the cold like we do with the heat. With the heat, we can adapt to the hot air. Our hypothesis was the subjects will choose a higher rate of perceived exertion in a hot environment over a cold environment.
For our methods we use repeated measures ANOVA via Excel and found p-value. We also found the averages based on the time of each subject, and we found the averages of the sessions, meaning hot versus cold environment. The hypothesis was answered based on the p-value. Our results showed, according to figure 1, average of RPE values in hot and cold environment. The graph shows in green hot sessions and in blue cold sessions. As you can see, during the hot sessions, the subject reported as on average a higher RPE ratings than the cold sessions. The average hot session was 4.75 with the average cold session of 3.13. According to our p-value, which is less than 0.05 and is 0.004, concludes that we accept our hypothesis that the subjects would choose a high RPE rating in a hot environment over a cold environment. You can also see that the pre and 3-minute post area for both hot and cold sessions were 0, meaning the graph did not show up any colors related because they were at 0 RPE rating values.
Physiologically, why? Physiologically, why? Cardiovascular, respiration, muscles, psychological, and the central nervous system all play a role in trying to keep the body in homeostasis. So starting out, the cardiovascular, the body will send blood to circulate through the skin, which in hopes will try to cool the body down. Along with that, there will result in less blood in the muscles and the increase of heart rate. So if the muscles don't have the needed blood or less blood, it'll cause them to feel almost fatigued or just plain out tired. So then with the muscles feeling fatigued and tired, it will play a role in the psychological, where you are telling yourself that you're tired and you can't go anymore, along with the thermal comfort. So when your body is overheated, you don't feel comfortable in that state and you want to change and cool down and yes. The central nervous system will also play a role in this with the temperature. So the hypothalamus is the main homeostasis, will create homeostasis, and that is central in the central nervous system. Along with that, all of that, the body will also create sweat, which is a form of evaporation. And this will go on top of your skin to try to cool your skin down and in hopes of bringing your homeostasis back down or bringing your body temperature back to homeostasis.
In our article, Associations Between Thermal and Physiological Responses of the Human Body During Exercises, they had basically a test chamber, and it was 70 degrees Fahrenheit with a 64.5% humidity. They separated 11 subjects. These subjects had no smoking, alcohol, or substance addiction. They also had experience in athletic training and participated in formal exercising over the 5 years rather. They were put into a heat recovery system and an electrical heating system, which heat recovery system is basically channels fresh air and blower fans and exhaust air. The electrical heater system basically converts the electric current into heat, and the participants were basically graded on their sub-maximal exercise test, which they performed a 4 or 5 minute stage of continuous workout until respiratory threshold was reached. After 30 to 45 minutes of the graded submaximal exercise test, the maximum oxygen consumption tests were performed, determined by aerobic power of each subject and instant load of VO2 max. Test was set to a respiratory threshold, and which ended up meeting the submaximal exercise test. The researchers analyzed their data by using SPSS, which is a software statistical data. The results showed that the average RPE value started from 6 at the beginning of the exercise and increased throughout the exercise. And also, the results showed that the RMP was higher in a low aerobic power group than the higher level group.
Okay. Taylor, you got it figured out now? Okay. Unmute yourself though. There you go.
Every time. Okay, now it's saying it again for this one. I just was listening to. Okay. This is our presentation that C and I did.
Do you want to email it to me? Maybe it's your computer or something?
Can you guys hear it okay? Or?
No. So you have to share. Was the sound working for you?
Yeah.
Oh, okay. So just when you share your screen, there's a spot where you can click like share audio or something. So go to new share for your screen, and then when that box comes up, I think it's in the lower left corner. There's like a spot where you can check mark share computer audio.
Okay.
Let's try that. Or you have to request that for each slide. That's weird.
So, yeah, that's why she sent me like 3 of them. there's 2 of them, but she sent me like 3 acceptances, and I was just listening to them. But we can at least listen to the first one. I think she's working on the second one right now. So sorry about that.
So before we delve deeper into this particular study, I just want to give a little introduction to some of the key points that we were really focusing on throughout the entirety of this study. So first off, we really looked into homeostasis, and we've discussed this pretty extensively in lecture, and it's also defined in our textbook as a relatively stable condition of internal environment that results from regulatory system actions. And then we also look deeper into core, which is deep central tissues monitored within a small temperature range. And I'll talk about that temperature range later on in this slide. And then also shell, which is the body's periphery. And this is much more variant in temperature in contrast to the core. So body temperature is a major factor that homeostasis works to regulate and maintain throughout the body at all times. And so when the body is introduced to new extreme environments, these physiological mechanisms then are activated to ensure the body still is able to stay within the optimal range for proper functioning. So, for example, when the body becomes too hot, these physiological processes kick in to ensure that the body still stays within that optimal range. So some of the mechanisms that are deployed are sweat is released and then evaporated off the skin surface, which helps to release heat. And then also blood vessels that lead to the skin capillaries widen or dilate, which in turn helps more blood flow through the skin, and then heat is lost through that. On the other hand, in cold environments, physiological processes include muscles contracting more rapidly, which causes shivering, and these contractions need energy from respiration, which also releases heat for the body to utilize to stay warm and keep that core temperature regulated and maintained. And also blood vessels that lead to the skin capillaries are constricted in this cold environment, and this also helps to conserve heat within the body and again maintain that core temperature. So homeostasis has a major relationship regarding the maintenance of temperature within the core and the shell of the body. So like I stated earlier, while the shell is much more variant in temperature, the core is monitored within a very small temperature range of between 36.5 to 37.5 degrees Celsius, or if we alter that to Fahrenheit, it would be 97.5 to 99.5 degrees Fahrenheit. So this temperature of the core is tightly regulated by the hypothalamus in the brain, and the hypothalamus senses changes in the core temperature, and then essentially it operates as a thermostat within the body to activate physiological mechanisms for whatever conditions are present, whether it be a cold environment or a hot environment, whatever it is. So, like I stated, while the shell does have a wider variability in temperature, this helps to regulate the heat transfer from the core to the outside environment. And then the core, on the other hand, is kept at a small temperature range. And when this temperature range is maintained, the proper physiological processes can occur efficiently and optimally at all times within the body, which is obviously a necessity. So during this lab, we had a few different viewpoints and assumptions on what would occur within the shell and the core during both the hot and the cold environments. So in the hot environment, we assume that the core will maintain its normal temperature range. However, we think that the shell will increase in temperature depending on the intensity of the exercise the subject is completing. So we are thinking about it in our own lives and applying it to our own lives. When we complete a high intensity workout, we feel warmer, we sweat more, and so that kind of helped us assume that the shell of our body would increase in temperature in a hot environment. On the other hand, however, in a cold environment, again, we assume that our core will remain pretty much maintained between 97.7 degrees and 99.5 degrees Fahrenheit, but we think our shell will decrease in temperature in association with the cold environment outside. So our research question was that what were the physiological changes that occur in a hot environment versus a cold environment? And so with that question in mind, we then were able to figure out a purpose for the study, which was to compare physiological changes within a stimulated hot environment and then a stimulated cold environment. For the methods we took to conducting the study, we first started out with subjects and they completed 2 sessions. One session was a hot environment simulation and the other one was a cold environment simulation. The cold session was completed 1 to 2 days after the hot session in order to ensure full recovery for those subjects. The hot session utilized a sauna suit as well as a stocking cap, and the cold session used lightweight shorts and tank tops as well as ice packs situated methodically throughout the body, including in a baseball cap as well as in a sports bra, granted if they were a female. The subjects then walked on a treadmill starting at low intensity and gradually increasing to moderate intensity throughout the span of the exercise phase. And during this exercise, heart rate, workload, and RPE, or rate of perceived exertion, were measured prior to exercise and then every 3 minutes during until a maximum of 18 minutes, and then again 3 minutes post-workout in both simulations. After we had our data, we then used a repeated measures ANOVA for this data set because this type of testing is used when all members of the study are tested under a variety of different conditions. In the study, the subjects were tested in both hot conditions and cold conditions, and then a variety of factors were measured throughout, including heart rate, RPE, and workload.
So, as Tia mentioned before, we tested the physiological differences between the hot and cold temperatures. So, the results of our RM ANOVA are as follows. So we just kind of took each portion of it and kind of broke it down a little bit. So this first graph shows the changes in heart rate between the hot and cold environments. And as you can see here, there's some overlap here, and then there's some significant difference maybe between the inside and then down below. But unfortunately, we are just shy of being significant at a 0.07 value. Further study would be interesting to see maybe between the differences between maybe 6 and 18 or even 6 and post, but I think that Tia and I talked about maybe that this was kind of what was getting in the way of that. So based on what we see here, our p-value is not significant at 95%, but we can allude that maybe it is significant at 90%. But again, further testing would potentially produce positive results. It also shows here that our F value is smaller than our F critical value, so it's just further validating what I just said. Sorry, one thing I forgot. So as you can see though, just to take note and just a general trend here, we do see, we can't say with significance, but we can see that just generally the trend here is that it's a little higher in the hot temperatures and a little bit lower with the cooler temperatures. And I'll talk more about that in a little bit. So next, just the differences in the RPE between the hot and cold. Again, unfortunately, we did not find any significant difference here, but we can note that at least the trend here that, again, the hot is a little bit higher throughout the process than the colder environments, as you can see here. So I think that some of this may be in part of our sample size and maybe just some testing done at home, etc. So I think it would be interesting to see what maybe the results would be like in a class setting, and maybe, excuse me, if we had some more subjects to test. I think that would be interesting. And then workload was not found to be significant as well, just because the inclination wasn't increased in one of them, so we had problems finding significance with that value as just taking a look at the discussion overall. So we did note that the heart rate was a little bit, although we can't say significantly, at least the trends to kind of touch on for physiological reasons was higher in the hotter environments than the cooler ones. And so this is just because physiologically, we really don't have much to fall back on. For example, in the slide, sorry. So when looking at here, this is just different physiological changes that happen within the body. And just to note that on the cooler side here, there's kind of some more things that are happening rather than the hot side. So the hot side, there is more mechanisms that are happening within the body to keep closer to homeostasis, so these other things don't happen. So I'm just here showing just the trend of the two, that you see how many more problems happen within the cold temperatures than the hot temperatures. And that's just because of just the different ways that our bodies handle the two different environments. So as we heard about in lecture, the cooler environments, the hotter environments, it starts off the activity. We start off with the activity. So the first thing is that we need more oxygen to our tissues. So we need to increase, decrease stroke volume, decrease cardiac output, and then decrease venous return, so that the heart rate then can increase, delivering more oxygen to our tissues. And then in response to that, because it is a hotter environment, we need to cool off our inner organs so we can maintain that very small range of homeostasis that Stia was talking about. So how do we do that in a hot environment? So what our body does is that we vasodilate, and we can deliver more more blood to our peripheral appendages and the outsides of our bodies to go to more of our shell region, and we can just disperse that a little bit better, and so that the heat can have a greater surface area and then can evaporate into sweat, etc. So again, the body has more mechanisms in this point here than with the colder environments. It just it doesn't have as many things that it can treat these problems that are occurring here. So remember, physiologically, we just generally have more mechanisms to fight the hyperthermia rather than the hypothermia. So we can touch on some of the trends here, which is kind of what the trends were saying a little bit, although we can't say it's significant. I think that maybe if we redid it a little bit, that maybe it might be different in the future, but it's kind of interesting to just touch on those trends for physiological reasons. So again, as I was talking about, so as activity increases, that oxygen, we need more oxygen for our muscles. As heart rate increases, the stroke volume, etc., decreases, like I was talking about. And again, the heat is dispersed away from the body via blood, and then it's achieved by vasodilation. And again, body just struggles more in the cooler environments. So when we're connecting it to the real world, the paper that I found was a paper that is using the core temperature and the shell temperature to predict an environmental a response to the environmental what's going on in the environment. Excuse me. So the military was trying to develop this HSDA, which is a heat strain decision aid. So it would be a military application just to kind of predict like some physiological changes in relation to like global warming, or like where troops are going to be sent, what kinds of things they may be dealing with, which I thought was kind of interesting. And then they use that to then touch on how these different things are changing in response to the environments. So again, like when we talked about in class, like they use the factors that contribute to the heat loss, like the body, or the using clothing, body size, environment, which included examining the humidity, wind velocity, and air temperature. to then come up with kind of a score that would be this HDSA. And it's kind of confusing in the sense that it's kind of an more abstract idea with this HSDA, but just kind of think of it as kind of like a grade for, Dubuque, Iowa, or the middle of the desert, or Antarctica, right? So just don't pay too much attention into that. But what you should focus on is that they're using these factors that attribute to heat loss to kind of examine what's happening physiologically. So their hypothesis was that they could determine work rest maximum, maximum one-time work, and then determine clothing for certain environmental conditions, and then to use that to see kind of what's happening between the different environments. So this is really confusing here to start off with, but my whole point of adding this in here was only just to show that how much went into mathematically, like what they were looking at. So I thought that was kind of interesting. But you can see that they're using the different environmental aspects of the environment, the different height and weights in each of the individuals, a lot of different information that is their workload, etc. And then kind of coming up with this sweat rate eventually, and then a specific time point in which he is dispersed. So just take that away from that. And then again, I thought this was kind of interesting that they, within their methods, are very meticulously going over these different environmental conditions, biophysical characteristics, and physical activity, just to kind of give each person a good look over of what they're doing, and then their different hydration levels, environment, clothing, the different work that they're doing in their activity, and then their sweat rates, their core temperatures, and then they're getting these different kinds of readings out in the HSDA score, excuse me. So overall, what they found is they had a sample size of about 75 people, and they determined that there was a difference between the hot and colder temperatures, just based on this HSDA score. So what they did find is that the HSDA score was lower in colder temperatures, and that overall heart rate and work was about lower than the hotter environment. So these subjects were working a lot harder in the colder environments than the hotter environments, just because their bodies are struggling physiologically to kind of keep up with all the problems that we've seen in that one slide. Just the problems become too much that the body fatigues faster than the hotter environments. And they really touched on this paper about the differences in gender, which I thought was really interesting in bringing back to our class material. They did find that the women had a greater heart rate and sweated less than men, which was pretty interesting. And then the men had an increased heart rate and generally sweated more, which contributed to them becoming more dehydrated and becoming more fatigued than the women. So again, for us. But so yeah, I thought that paper was pretty interesting in the way that they could quantify exercise physiology, and I thought it was an interesting approach to kind of divulging into our topic. So I chose that one. So here's our references, and that's all.
Awesome.
How do I unshare? Oh, there it is.
There we go. Okay. Any questions from anybody about yesterday's lecture, brain and conscious behavior, or your ex-phys projects? Is everybody okay on what's happening?
I have a quick question about mine for the Physiology Lab.
Yep. You cut out.
So we're doing like the arm circumference and like grip strength. Can
Yep.
I use like a person's each arm, so like that counts as like two, like each person could have two like data because like there's two different arms, or is that not okay?
Yeah.
Do I need 10 different people?
I still think you should use 10 people, but having 20 data points would be good.
Okay.
Yeah.
Just
Any
gotta
other?
find people.
Well, you got parents, you got, you know,
I'll also make people at my work do it.
yeah, there you go. It only takes a second.
Yeah.
Be too bad. Other questions?
I think we did too. Valerie should just ask them now. So we were kind of getting confused, like just between like our experiment. And I seen your email yesterday, and so so we were kind of thinking, going back and forth between like, let's see, what's that?
Was it like heart rate and like maximum number of push-ups?
Yeah, I was not sure what you guys wanted to achieve. So we got to have maybe a little bit more of a clear purpose. So do you want to know what their maximal muscular endurance capacity is, or because again, that can be unrelated to heart rate, or not directly related, I should say. They're related. Yeah, I felt like you guys are trying to do a few different things, and we're not really 100% sure what it is that you want to find out.
Okay.
That's kind of where we were at too. But Valerie and I can meet again. Are you okay with that, Valerie? And then we can come up with a better email to you, Dr. Beckler.
Mm-hmm. So yeah, so remind me again. So you wanted to look at running a mile and maximum push-ups, right?
Yeah. Yep.
So the way I first read it, I thought you kind of wanted to figure out like, okay, does aerobic exercise negatively impact the amount of push-ups that I could do versus, because then you had another section where they did stretching and then the push-ups. So I thought, okay, is that what they want to see?
That's kind of what I was thinking. As far as like, I think it was just as far as what everybody else was thinking as far as that. So we'll definitely like talk more about it and like get something in today.
Okay, yeah, just a little bit more clear on what your hypothesis is and what you want to know, if that makes sense. Keep it simple. You don't have to make it super, like you got a bunch of different things going on. Just
Okay.
I think that was our problem. So we'll try again.
choose one thing to look at. Just keep it simple. So Jess's group, they're doing arm circumference and grip strength is their relationship. So something simple like that, that would be fine. Again, you'll have to find 10 subjects, and so each of you will find 3 or whatever in order to get that done. So simple is better, and then it's easier to get people to do this too. That's the other thing. You're going to ask people to do a mile and a bunch of push-ups and stuff. Are they going to be like, no? So that helps if it's a little bit more simple or doesn't take too long or anything like that. So yeah, just send me an email. I plan to work all day today. So yeah, I'll be able to get back to you guys right away. Yeah, otherwise, we'll plan to send out a Zoom request for Tuesday night to do these presentations on Wednesday. I'll let you know either whatever's going on, either way, whether that's happening or not. So otherwise, yeah, you guys all have my cell phone number, and if you didn't, it's on the syllabus. Just text me if you do have questions next week if I'm not available via email, but otherwise, email or text is fine. I don't care, either one. All right. Okay. Have a great weekend, and I hope to see you guys next week.